In this video, we're going to take a look at the Acid Base Titration lab for grade 12 chemistry, AP chemistry as well. It's a three-part experiment involving titrations, a volumetric technique that uses stoichiometry. We're going to be, in part A of the experiment, standardizing a 0.1 molar solution of sodium hydroxide that we prepared. To standardize it means we're going to determine its concentration exactly to several significant digits. In part B, we'll use the sodium hydroxide solution, whose concentration we now know, to standardize a sulfuric acid solution. And in part C, we'll also use the sodium hydroxide solution, but this time to determine the molar mass of vitamin C, ascorbic acid. When you walk into the lab, you're going to find it set up with a whole bunch of glassware like this. So you can see here each station has what's called a burette set up at it, and you're going to be working individually for this experiment. I'm going to walk you through in this video how to do the first part of the experiment, and then we'll talk briefly about the remaining two parts. So this is my workstation. When I come to it, I'll find a burette already clamped in place like this to a support stand. There'll be a bottle of distilled water there, as well as a bottle that contains 500 milliliters of my 0.1 molar sodium hydroxide. That's what I'm given for the entire experiment, and I need to standardize that in the first part. So what I'll do first is prepare the burette. I have to get it filled with sodium hydroxide solution, but before I fill it, I'll have to rinse it 3 times with distilled water. So I've removed the burette from its support stand, and I'm going to just give it a rinse with 3 small portions of distilled water from my water bottle. So I'll just squirt some distilled water in, approximately 10 milliliters. You'll notice that the burette is calibrated, so I can tell approximately the volume that's in it. So I'll just put a little bit more water in there. Okay, when I've got about 10 milliliters of distilled water, I will put my finger over the top of the burette, and then I'm going to turn it on its side and rotate it so that the water covers the entire glass inside the burette. I've got my finger on one side here, and I'm swirling the burette. The bottom part of the burette that you see here with this yellow knob, this is called the stopcock of the burette, and there's the tip of the burette here at the bottom. What I'm going to do is turn the stopcock. Right now it's perpendicular to the burette, and that means it's closed. If I turn it so it's parallel to the burette, I think you can see now some water draining out of the burette. What I'm doing now is rinsing the tip of the burette as well. I don't have to wait for it all to drain. I can simply turn it over and drain the remaining water out through the top. So I'm going to repeat that 2 more times. Alright, I've just rinsed the burette 3 times with distilled water, small portions, and now I've got in this beaker about 100 milliliters, 80 milliliters or so, of the sodium hydroxide solution that I was given. This is what I need to do, what I need to put into the burette before I can begin my experiment. But right now the burette is full of distilled water, at least it's rinsed with distilled water, so the sides are wet. I don't want to fill it right now with this sodium hydroxide because the water in the burette would dilute the sodium hydroxide, and I'm trying to find the concentration of this sodium hydroxide, so I really don't want to dilute it. So what I'm going to do is rinse 3 times with small portions of sodium hydroxide. So the same way I just rinsed with distilled water, I'll put about 10 milliliters of the base into the burette, and then I'm going to turn it on its side again, and I'm going to rotate it to coat the entire inside with sodium hydroxide. And I'll do this 3 times. Now the concentration of this base is pretty dilute. I can actually do this and avoid having it touch my finger if I'm careful. But at this concentration, if a little tiny bit of base got on my finger, I really would just take a moment and rinse it off. It's not going to hurt me at this concentration. I'd feel the base is slippery. Remember, that's a property of bases. You could wear gloves if you wanted to really be careful. Now I'm going to also rinse the tip of the burette. So again, drain some out, turn the stopcock so that it is parallel to the burette. And then once you've rinsed the tip, just pour the excess out into your sink. And you're going to repeat that 3 times with sodium hydroxide. Alright, having rinsed the burette 3 times with sodium hydroxide, I've got my beaker again of sodium hydroxide, and now I'm going to fill the burette past the very top mark on it with the sodium hydroxide solution. So I'm just pouring in, keeping the burette at an angle, and I'm going to fill it all the way up past the very top mark on the burette. Now, the burette, the first time you see it, you're going to be perhaps a little bit confused, because when you look at the markings on it, and I'll see if you can see this in the video, you'll notice that the markings at the top start at 0 and then go down 1, 2, 3, 4, all the way down on this burette to 50 milliliters at the very bottom. So the reason the scale is like that is because we're going to be measuring how much liquid we drain out of the burette as we do our titration. So initially, I've put in enough sodium hydroxide so that its level is above the 0 mark on the burette, and now I'm going to drain some of the excess sodium hydroxide back into the beaker from which I was just pouring. But as I drain it, what I want to do is take a look in this tip. I want to be sure there's no air bubbles in there. So here we go. We're going to drain the excess. I don't see any air bubbles. And looking up at the top of my burette, the level is now below the 0 mark on the top. So now I'm ready to use it. So I'm going to clamp it back into its support stand, and then I'll be able to prepare my flask with acid. So I'm clamping it back into the support stand. I'm turning it so that I can easily see the scale in front of me, and now it's ready to go. I'm now standing at the electronic balance, and this is the milligram balance, so the reading on the balance goes to 3 decimal places. And I'm going to put some acid. The acid we're going to use is called potassium hydrogen phthalate. There's its name. And it's an acid which is monoprotic, so it has 1 hydrogen in its formula, and it has a molar mass which we're going to need later of 204.22 grams per mole. I'm going to use about 0.5 grams of the acid in each trial of my titration. So what I've got is a piece of weighing paper, which is a waxy paper. I'm going to just fold that in half and make a crease, and then I'm going to unfold the paper, and I'm going to place it on the electronic balance. And now I've got the bottle of KHP. I'm going to remove the lid, and using a scoop, holding the bottle directly over the pan of the balance, I'm going to add enough KHP to get me approximately 0.5 grams. I don't need to have exactly 0.5, but what I want to do is record exactly the mass that I've used. So the mass on this balance right now is 0.508 grams, which is pretty good. I've got here an Erlenmeyer flask, 125 milliliters, and I'm just going to take the paper, which I creased, and pour the acid into my flask without spilling any. Now the crease allows me to do that easily, and the paper is waxy so that the acid won't stick to it. The paper will just go in a waste container, and now I've got the acid added to my flask. If I spilled any, I would have to dump that acid out of the flask and start again. So I'm back at my station, and I've got the flask with the acid solid in it, and I'm going to take some distilled water, and I'm going to add just enough distilled water to give me about 20 milliliters. There's markings on the side of the flask that I can estimate that. The exact volume is not critical, and what I need to do now is swirl to dissolve that acid completely. Not a single grain should be left undissolved. And as I swirl, I can tell that some acid is getting up on the sides of the flask. So what I'll do periodically is take my distilled water bottle and wash that acid back down into the water. But what I want to be sure is at the end I don't have an excess amount of water. It would be ideal to have at the end about 50 milliliters plus or minus maybe 5 or 10 at the start of the experiment. So I'm swirling, swirling, swirling. KHP, because it starts with potassium in its formula, should be highly soluble, but unfortunately it doesn't dissolve quickly, so you'll have to do this for a while. What you might want to do is get it added to the distilled water first, if you have time. As it sits in the water on your bench, you can be preparing your burette, and it will be dissolving as you go. Some people use a stirring rod. There's stirring rods in your drawers. If you took a stirring rod, you could crush some of the acid. If you do that, though, that'll actually grind it to a finer powder, make it easier to dissolve. But now I've got acid on the stirring rod, so what I would have to be sure to do is use the distilled water bottle again and just give the stirring rod a small rinse before I take the rod out of the flask. This is a quantitative experiment. You don't want to lose any of that acid that you put in there. Now, we weighed it out at the electronic balance with a milligram balance, and we recorded the exact mass to 3 decimal places on our data sheet. So I've got the acid now completely dissolved. I'm going to grab another flask, which is actually already ready to go. And now I'm almost ready to start the titration. Notice that the acid dissolved in the distilled water is kind of boring. It looks like water, colorless liquid. And notice that our sodium hydroxide in the burette is also looking kind of boring. It's looking like a colorless liquid. When we add the two, the reaction is going to be somewhat boring. It's going to look like adding water to water. So what I've got here is a special chemical called phenolphthalein. It's phenolphthalein indicator. And what it's going to do is let me see the reaction happen as I put the base into the acid. I'm going to take some phenolphthalein and put about 3 drops, approximately 1, 2, 3 drops, 3 or 4 drops into the flask. When you do the experiment, phenolphthalein will be in the fume hood, and you'll use a little plastic pipette to put the 3 drops in. Notice that phenolphthalein in acid is colorless. When we put phenolphthalein into a base, let me just illustrate that. I've got my beaker of sodium hydroxide here. I can just waste it and to illustrate. I'll put phenolphthalein into the base, 1, 2, 3, and notice that the color turns instantly pink. So phenolphthalein in a base is pink colored. Phenolphthalein in an acid is initially colorless. We're going to be adding base to this acid. So eventually the color is going to turn pink, and that's going to tell us to stop titrating. Before we can begin actually titrating, we need to record the initial level of sodium hydroxide that's in our burette. Now for the video, I've lowered the burette all the way down so that the video here camera can see that, but you would just do this at eye level. Be sure that you're looking exactly at eye level, not from below or not from above. If you have to, you can bring your burette closer to the bench, to the side of the bench, so that you can lower it to get down to eye level. Now you can tell right now that the meniscus, which is right here, is between 0 and 1. So I'm going to record on my data sheet that the initial level is 0 point something. The exact number is not important. It might even have been below 1. Maybe it was 1 point something or 2 point something. But right now on this burette, it's between 0 and 1, so 0 point something. Now maybe in the video you can actually see that the meniscus is past the 5th tick mark. So we're counting down from above. It's past point 1, past point 2, past point 3. It's past the 5th tick mark. Now, it gets a little hard to see the meniscus because of the way the light interacts with the water. So I've got here a card, and this is a fancy little titration card. You could do the same thing with any piece of white paper on which you've drawn a black stripe or a heavy dark stripe. What I want to do is hold that behind the burette so that the black stripe is below the meniscus, as you can see there. And I would be looking at it from the perspective of your video. And now if I raise or lower it, what I should be able to see eventually, if I hold it steady, is that the meniscus looks like it's now traced with the black from that stripe, and it's against the white background of the card. And that will let me see the meniscus more clearly. Remember, since grade 9 science, you've been taught to look for the very bottommost part of that meniscus. So you can see a curved surface. You want to look at the very bottom of that curved surface, the lowest point. So when I do that, it becomes very clear that it's between the 5th and 6th tick mark. So it's between the 5th and 6th graduation. So the volume level is 0.5 something. And now I'm going to estimate, so I can look very closely. I can see that it's a little bit closer to the 6th tick mark, the 6th graduation. So what I would do is estimate 0.57 as my initial level. Now if you saw 0.57 and I saw 0.58 or 0.56, we would be agreeing. We wouldn't argue over that. We would write down any one of those numbers. But if I say 0.57 and you're seeing 0.54, Well, we might actually take a closer look, because now I'm seeing that it's closer to 0.6, but you're thinking it's closer to 0.5. We should be able to come to an agreement about that. So remember to look at eye level. Remember to use the card held behind the burette so that the black stripe is below the meniscus, and then raise or lower it until the meniscus appears like a thin black line against the white background. That should let you see it clearly. Notice too that the graduations on my burette are right in front of my eyes, so I can easily read those the volume level. A common error is to report the volume that they think is in the burette. I'm not trying to report how much liquid is in the burette. I'm simply recording the initial level of the sodium hydroxide in the burette. So this initial level would be 0.57 milliliters. We're now ready to actually titrate. We've got our KHP acid dissolved in the flask completely in distilled water. We've washed the sides of the flask down with a little bit of distilled water to be sure all the acid is in the solution. I added 3 drops of phenolphthalein indicator so that I'd be able to see a color change during the titration, and I recorded the initial level of sodium hydroxide in the burette. So now we're going to add the sodium hydroxide to the flask. Now I'm right-handed, so what I do is I hold my flask with my right hand and I operate the stopcock with the left hand. And notice I wrap my hand around behind the burette and grab hold of the stopcock with my fingers. And now I can open the stopcock and let some sodium hydroxide drain into the flask. And as it drains, I can swirl in a circular motion the flask. I'm swirling gently. Now the problem with this first trial is that I have no idea how much sodium hydroxide will be required. As the sodium hydroxide goes into the flask, it is neutralizing the acid. The NaOH reacts with the acid, which is monoprotic, in a 1-to-1 ratio. Now eventually there'll be no more acid in the flask. The very next drop of sodium hydroxide that I add will cause the color in the flask to go from colorless, like it is now, to pink. Now a good ending is not a really, really dark pink. If you get a really dark pink, you probably added too much sodium hydroxide. So what I want to do is add just enough, not a drop more, not a drop less, to make this solution turn pink. When I've done that, the sodium hydroxide will have completely neutralized and exactly neutralized the KHP that's in the flask. The problem is I don't know in the first trial how much to use. So what I'm going to do is waste my first trial. I'm going to simply let it drain in, and you can see the pink color appear in the solution, but then when I stop and swirl, the pink color disappears because it neutralized the acid right where it went in, causing the pH to rise. It changed color there. When I swirl, the excess acid from the outside comes back in and the pH drops and turns back colorless. But eventually there'll be no more acid in the flask, and as I get closer and closer to the ending, the pink color persists longer and longer. Now in a good ending, this is what would happen. This is called the end point of the titration. I would have a colorless solution like this, and using the stopcock, if I'm very careful, I can put a single drop in. See if you can see a single drop. See if I can actually do that on a video here. There we go. 1 drop went in. Now technically, there's a little tiny bit on the end of my burette, so I'm going to have to add that. It's going to be about a drop and a half. I'll reach in and touch that to the side of my flask. Using distilled water, I'm going to wash that in as well. I'll also give the sides a wash to make sure everything is back in the solution. Now in a good titration, that 1 drop would have caused the color in the flask to turn pink, probably a faint pink. Then I would stop the titration and record the final level of sodium hydroxide. Now my rule of thumb is if it stays pink for about 10 seconds of swirling, you're done. Okay, now when you put the flask down, as it sits and reacts with CO2 in the air, the color may fade. Phenolphtalene's color actually also does fade slowly over time just on its own in sodium hydroxide. So if it stays pink for 10 seconds of swirling, you're done, no matter what happens after that. So what I'm going to do is just keep going in this first trial, and I'm not going to try to be very, very accurate. I'm not going to try to get one drop turning it pink. I'm just going to keep going here. I'm adding more. Okay, I'm opening and closing the stopcock and closing it until the pink color stays. So open, close, and oh, that's very close. I could actually almost use this because I'm very close. Okay, in a normal titration, what I might do, it's colorless. I'll rinse the sides down with distilled water. In a normal titration, what I might do is get it dripping at a nice steady drip. Watch this. So I'm going to count it out. Drip, 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 like that. And then I should be able to stop and have it turn pink like this within one drop. I think that was probably within 2 drops. That's still probably pretty good. Notice the color is faint pink, it's not dark pink. If I went much further, then it would have turned into a much darker pink, and that's generally not a good end point. Alright, so in my first trial, which I probably won't keep, I'm not going to probably use the result, I've now added enough base to cause the color to turn pink. What I'll do now is lower my burette to eye level. Okay, if I'm shorter. So we've reached the end point of the first trial. The flask turned pink, and now I'm going to read the final level. The meniscus is clearly below the 26 milliliter mark, but it's not yet at the 27, so it's 26 point something. It's very close to 26. Holding the card behind, again with the black stripe below the meniscus, and then moving up or down slightly, I can read the bottom of the meniscus to be actually very close to 26, but not just a little bit past, not quite 26.1. So looking very closely, it looks closer to 26 than to 26.1. I'm going to estimate 26.02 is my final volume reading. So now let's think about what we've got. Here's my data sheet. We recorded the mass of KHP, 3 decimal places. We used 0.509 grams if I recall. We would have recorded it here on the data sheet. We recorded the initial and the final level of NaOH in the burette. And now let's take a look at the results section. The molar mass of KHP was given to us, 204.22 grams per mole, and that will be the same in every trial. And remember that it's a monoprotic acid and that it reacts 1-to-1 ratio with our sodium hydroxide. You could write out a balanced equation representing KHP as HA and let it react with NaOH, and you'll see it reacts in a double replacement reaction 1-to-1 ratio. Now, since we know the mass and the molar mass of KHP, we can find the moles of KHP using a formula: moles equals mass divided by molar mass. The moles of the NaOH, because of that 1-to-1 ratio, would be the same as the moles of KHP. So if I know the moles of KHP, the moles of NaOH would be the same. Now, the volume of NaOH that we used in the titration, well, if the initial level started at some number and the final level finished at some other number, then if we subtract those, we know the volume of NaOH that was used, and that will be in milliliters. If we convert the milliliters to liters, we now know the moles and the volume in liters of sodium hydroxide in this trial. So now we can divide them, C equals N over V, to get the concentration of sodium hydroxide. The first trial was done quickly, so it's probably not going to be a reliable trial. If we took a fresh sample of KHP dissolved in a fresh sample of water, we recorded its mass to do trial 2, and we go to our burette and we refill the burette and record a new initial reading, so here's our burette refilled, we could now, if we used approximately the same amount of acid, we could simply let it drain quickly. Now remember to add your indicator, 3 or 4 drops. We can let it drain quickly until we're pretty sure we're within 1 or 2 milliliters of the end point. So for example, if we found out that it took 25 milliliters in trial 1, well, it should take 25 milliliters in trial 2. What I could do is just drain very, very quickly until I've let in, say, 23 milliliters. Now I know I'm very close to the end point. Then I can do drop by drop, like I showed you a minute ago, until the color turns faint pink. That way I do a very quick initial part of the titration and then a slow, accurate part of the titration at the end point. So now I will repeat the experiment 3 more times at least. So I want to have 3 trials with good results. And then I can actually stop and say what the average concentration of sodium hydroxide was. When I have that, I will now know what the sodium hydroxide's concentration is, and I'll know it very accurately, so I will have standardized it. I can now use that sodium hydroxide in part 2 of the experiment to analyze sulfuric acid, and in part 3 of the experiment to analyze vitamin C. Essentially, we're going to replace the KHP in part 2 of the experiment with sulfuric acid, and we'll replace it in part 3 of the experiment using vitamin C. There's a little bit of a description of each part of the experiment, and you should be able to complete this, each part in about an hour, maybe slightly under an hour, and you'll have 3 classes to do this.